Good afternoon, y'all. Bad news. My camera's not working right now, so hopefully I get that figured out before I make the next video. But for right now, I'm just a disembodied voice. But welcome, it's Miss Johnson. A little bit of calculus. All right, I'm going to go on this thing I'm calling a plus C rant, just to talk about the memes you see on the internet and the classes you'll take in the future and what this means. And then I will go over the fundamental theorem of calculus. We did get to these in 5th and 6th period and did not in 4th period. So if you're in 4th period, you do need to hang around for this. If you're in 5th and 6th and understood class, you're good to check out after this plus C rant. Here's what's going on. If we do the power rule, so we've got this question where it's what's the integral of 10 x to the 4th dx, right? We do the power rule. We say it's x to the 5th because we added 1. We divide it by 5, and we end up getting 2x to the 5th. Nice. We're diligent students, though, and we want to check our work, right? The way we check our work for an indefinite integral problem is you take the answer and you take the derivative of the answer. And if the derivative of the answer is equal to our original equation, then we've done the problem correctly. Let me say that again. If derivative of your answer equals the original problem, we got it right. Nice. Let's check our answer. By that I mean, let's move this one down a little bit. Let's check our answer. What's the derivative of this? We use the derivative power rule where we do the coefficient times the exponent, and then we move this down by 1. We get 10x to the 4th, and we're crushing. Great. You might ask, Miss Johnson, what's the problem? There's no problem. But what if instead of 2x to the 5th, I said my answer was 2x to the 5th plus 5? You'd say, where did you get the plus 5 from? That can't be right. I'd say, let's check it, right? Let's take the derivative of my answer. I'm going to say, what's the derivative of 2x to the 5th plus 5? I say, okay, well, for this one, you do 2 times 5 times x to the 4th. And for this one, you do 5 times 0 x to the negative 1, or sorry, times 0 x to the negative 1, because 5 is able to be written as 5x to the 0. And then I say that is 10x to the 4th. This goes away to 0, so it's nothing. And I just said my answer is right if it equals the OG problem, and it does. So it's a little bit of a mystery, right? If we're doing the antiderivative, and we're saying if we check our work, it's right if we take the derivative and we get our answer, then I should be able to add 5 on the back and it not be a problem. In fact, I should be able to add anything on the back and it not be a problem, because the derivative of any number is 0. So I think this actually has a whole host of answers that we could say is correct, where the base is always that it's 2x to the 5th, and then we can just add in any old number to the back. The way we write adding in any old number to the back in math is saying plus c, where c is a constant, aka any old number. So technically, when we take these derivatives, and you should do this on your worksheet as well, your assignment today, when we take the derivative of, say, 2x, or we take the derivative of 10x to the 4th, or we take the derivative of 7x to the 9th minus 10x cubed plus 7, or whatever, right? The answers are we take the antiderivative, as we've been used to doing it, but on the back, we add plus c for deference to the fact that if we had a constant there, it would just go away if we did the inverse, or if we did the inverse operation and took the derivative. So every indefinite integral problem. Should have a plus C at the end. That's my plus C rant. If you're in fifth and sixth period and you feel like you got this fundamental theorem stuff, you are good to check out now and do your homework. Otherwise, let's keep going. We're going to learn about the fundamental theorems of calculus now. All right, fundamental theorem of calculus 1. There's two parts to the fundamental theorem of calculus. One is a computationally very useful one, right? This helps us take definite integrals without using a calculator. And then the second part is a conceptually satisfying one, which to me means it's like beautiful and fun. Maybe you'll agree. All right. The computationally useful fundamental theorem of calculus is that for a function f, we're going to name its derivative as big F. So big F is the area function that we find using the indefinite integral. And the fundamental theorem of calculus 1 says that if we want to calculate the definite integral, we just take the indefinite version, plug in our top bound, plug in our bottom bound. So we plug in our b to the area function, we plug in our a to the area function, and then we subtract those two things. Pretty good. We're going to do some examples, and that's going to make more sense. Let's keep that up here and do the example here. The example is if we're doing the integral from 2 to 4 of 12x to the 5th, the first thing we do is find the area function by taking the integral. And here that is 12 over 6x to the 6th, aka 2x to the 6th. Then we've got some notation going on. Over here, we want our bounds to be 4 and 2. Once we take the integral, we want to keep that information handy. So we're going to put this notation where we put the bar and 4 and 2 to back our problem, so we can remember what we're doing. And then the next step is plug in the bounds and subtract. So here, I'm going to plug in 4 to my area. I'm going to plug in 4 to my area function. I'm going to plug in 2 to my area function, and I'm going to subtract those numbers. And then I'm going to plug it into a calculator, and I'm pretty sure it's 8046. Yeah, 64. Sorry, I forgot it from class. Cool. So that's how we find and this is the area underneath this function from 2 to 4. It's exactly 8064. Let's try that one more time. And let me drag this down. The first thing we do is we take the derivative, the integral. We write off to the back what our bounds are so we don't forget. Then we're going to plug these in. When I plug this one specifically in, I'm going to set up a pattern, like set up an organizational system beforehand, because I know I want to plug in 2 and then subtract the entirety of plugging in -3. And because there's 2 terms, we're going to have to distribute this negative, and I don't want to forget to do that. So I'm going to put parentheses. And now I plug in my top bound. I plug in my bottom bound. Nice. And then I plug this into a calculator where I do some math and I get 15. Nice. So the area underneath the function 14x plus 10 from -3 to 2 is 15. Again, computationally, this is a very useful function, or a very useful theorem. The fundamental theorem of calculus 2 is conceptually satisfying. Here's the math sentence, here's the English sentence. The math sentence says the derivative of the integral from a to x of f of t dt is equal to f of x. You might say, Ms. Johnson, you said this was beautiful. It is. The English sentence is basically the derivative and integral are inverse operations. Right? This is just saying that if you have a function and you take its integral, and then immediately afterwards you take the derivative, you just get the function back. It's saying that the integral and the derivative cancel each other out, and we're just left with the original function. This is the same thing for like multiplication. If you did 5 times f of t divided by 5, you'd get f of t, right? If you did same thing for addition and multiplication, or addition and subtraction. If you did f of x plus 10 and then minus 10, you just end up with f of x. This is just the statement that the integral and the derivative cancel each other out. We are going to do problems using the fundamental theorem of calculus 1. We are not going to do problems using the fundamental theorem of calculus 2, but both of them do need to go on your note sheet for the notes from the review. All right. Good luck with the assignment. I will see y'all on Friday, and if you have trouble, come to office hours, and I'll see you beforehand. Thanks, y'all. Bye.